In this video, we're going to focus on acids. We're going to remind ourselves what kinds of compounds are acids, and we're going to look at strong and weak acids and remind ourselves what we mean by those concepts. Okay, so if we go back into our naming, there are things that we named as acids, and there were some acids that we said that we should remember were strong acids. Okay, so one set of strong acids were the oxyacids, sometimes called mineral acids. Right? And so the strong oxyacids or mineral acids were nitric acid, right? Sulfuric acid, okay? And then if we keep moving right, stop it. My hand setting down on it keeps messing it up. Chloric acid, right? Chloric acid. And then remember, all of the halo acids below that act the same. So we had chloric acid, we had bromic acid, and we had iodic acid. Right? So those were considered our strong mineral acids, right? And so you should know those and you should recognize those as strong acids and be able to name them and write their formulas, all of those things. Okay? Now, there were some other mineral acids or some other acids of oxyacids that were not strong, right? So, right, sort of the special one is phosphoric acid. Right? Phosphoric acid, well, remember the strong acids, right? What makes a strong acid strong is strong acids dissociate, no, not strong, come on. Strong acids dissociate completely in water, right? So the ones that I wrote in yellow there dissociate completely in water. Phosphoric acid only dissociates about 85% in water. So it's stronger than most other weak acids, but it's not really a strong acid. But it's strong enough that we use it in the place of other strong acids. And then you've got the outlier in this group that is truly a weak acid, and we'll talk about it later, which is carbonic acid. Right? So you should know all of those acids. Okay? You should know all of those acids. Now, right? All of those acids that I showed there have names ending in ic, right? Ic acid, right? That means that they are the most common and usually fairly highly oxidized. They have a lot of oxygen acid in that group. Okay, now so let's remind ourselves, right? There are also acids that end in us acid, and they have one fewer oxygen atom. Let's finish writing my word fewer. Oxygen atom than the acid that ends in ic. Right? So, for example, we could do something like, right, if HNO3 is nitric acid, then HNO2 is nitrous acid. Okay? So, right, remind ourselves of our common acids and their naming. And we'll continue this because we have some more to talk about. Okay, so here's our view of our acids again. And if you'll look at our periodic chart, you'll notice that I've laid these out as they would be if the central atom, where the central atom would be on the periodic table, right? So, right, this is laid out relative to where the central atom would be on the periodic table. And we talked about, right, that there are acids with one fewer oxygen, right? And so if we go through here, right, as we have it laid out, right, that is weak, that is moderate, right, from what we said on the last one. And all those other acids in yellow are strong, right? Except I can't write my formula here. Make sure I get my formulas right and don't jump the gun. Okay, so we've got our strong acids represented there. And again, right, we've got nitric acid, we've got sulfuric acid, we've got chloric acid, we've got bromic acid, we've got iodic acid, right? Those oxyacids are strong. Phosphoric acid is a moderate acid. Carbonic acid is a weak acid, right? Now, we talked about those that end in us, right? So if we add those that end in us, right? Everything that ends in us is a weak acid. So HNO2 is a weak acid. Nitrous acid. H2 or H3PO3. Let me clean that up. Right? Phosphorus acid. H2SO3. Sulfurous acid. HClO2. Chlorous acid. And then, right, there is a similar bromous acid and iodous acid. Oh, what the heck, right? HbRO2 would be bromous acid. HiO2 would be iodous acid, right? So those acids are all weak acids, right? And so that's another set. There isn't an equivalent us acid for carbonic acid, okay? So we've just added some weak acids. So we've got strong acids, those that dissociate completely in water. And we've got weak acids, those that don't dissociate completely in water and often dissociate maybe 10% or less in water. Now, just to continue our reminder, right, with the halo acids, we've got other choices, right? With halo acids, we can go down to HClO, right, another one. And remember that one we add the prefix hypo. So HClO is hypochlorous acid, right? So if we're breaking it down, the us says we're down one oxygen, and the hypo says we're down another oxygen, right? So the hypo and the chlorous take us down 2 oxygens. So there's hypobromous acid and hypoiodous acid. And those are also weak acids. Okay? Clear that out. Right? Now, also on the with the halo acids, we've got what color do I want to go to? I guess I can go. I think I've used all my colors, but I'm going to go red. yeah, I'll go red. Okay? There's an option with one more. And again, there's one for bromine and one for iodine, right? I'm running out of space here. And remember how we named that? Right, now let's change to BrO4, right? So that is per bromic acid, right? So we've got I don't know what I did there. All right, so we've got perchloric, perbromic would be in here, periodic would be in here, right? And so per is telling us we have one more oxygen than would normally be found in the acid that ends in ic. And those per halo acids are also strong acids. So we just added 3 more acids to our strong acids list. Okay? So you need to know those strong acids, right? So, right, which are our strong acids, right? Nitric, sulfuric, perchloric and chloric, perbromic and bromic, periodic and iodic are our strong acids. And then we always have to remember the special case of phosphoric as a moderately strong acid. You should know all the other acids on this page as weak acids. Our next group of strong acids, or our next group of acids, not all of them are strong, are the hydrohalo acids. Right? Our hydrohalo acids are HF, HCl, HBr, and HI. Okay? Now, if any of these are appearing in the gas phase, so let's consider this, right? So HF in the gas phase would be named hydrogen fluoride, right? Hydrogen fluoride as a gas, right? It's only when we put them in water that we name them as acids. And so pay attention in naming, right? Depending on the state, the name changes. If we put it in water, then that becomes hydrofluoric acid. Okay? And so this is where there's some confusion in the naming. If you have hydro and ic with a halogen name, that's telling you there's no oxygen, right? It's just HF, okay? So hydro really is your clue not to put oxygen in the formula, okay, for these halo acids, right? So we've got hydrofluoric, hydrochloric, hydrobromic, hydroiodic acid, okay? Now, right, it ends up that the ones I put in yellow here, right, let's put our box in white here, hydrochloric, hydrobromic, hydroiodic. That is, when we put them in water, and let me get that in there, in water, they all act as strong acids. Okay? Hydrofluoric, because the fluoride ion is so small and the attraction is so high between the hydrogen ion and the fluoride ion, hydrofluoric acid is a weak acid in water. It does not dissociate completely. So we need to know our hydrogen halides and our hydrohalo acids, right? And remember how we distinguish the names for those acids from the names of the oxyacids that we covered on the previous slide. There are some other acids that use that hydro blank acid pattern in naming, right? If you look at an ion like the cyanide ion, right? If you put the cyanide ion, right, the negative charges on the carbon, right? If you put the cyanide ion in water and you make this as a gas, it's hydrogen cyanide, right? A deadly poisonous gas. But if you take that hydrogen cyanide and dissolve it in water, you make hydrocyanic acid, right? Similarly, if you take this ion, right, the N3 ion, which is called an azide, right? That's cyanide, right? If you make this, right, in solution, that would be hydroazidic acid, right? And note, right, we're taking off the IDE suffix, replacing it with ic, and then putting hydro in front to specify the hydrogen. And both of those are weak acids that we should know and recognize. Our last group of acids that we'll consider, right, that we need to know and be aware of are the carboxylic acids. Right, the carboxylic acids, right, carboxylic acids all have in common a structure that looks like this. Right, a group with a carbon with a double bond to an oxygen and a hydrogen, right, attached to some group that we will call R, right? And so carboxylic acids are common weak acids, right? There's a couple that we should be aware of, right? The carboxylic acid structured like this with a methyl group on that carboxylic acid group. It would have a formula like this, right? That's the way you would write it as a formula, right? That is acetic acid, right? And when we write these acid formulas like that, it is this hydrogen ion on the carboxyl group that is the acidic hydrogen the hydrogens anyplace else are not going to be traded in acid-base reactions, right? And so when we write the formula, we put the number of acidic hydrogens in the front. And then if there are other hydrogens in the structure, we put those in the middle of the formula to say that this acid can only deliver one hydrogen ion when it reacts with a base. Okay? So acetic acid, that is a formula you should know, right? Know that formula and that name. That's probably the most common carboxylic acid that we will deal with. But when you're taking biology classes, almost anything in a biology class that they call an acid is going to be a carboxylic acid. And it is going to be a weak acid. Okay? But this is the one you should be familiar with for this class. You should be able to know and recognize this formula, know this name. Okay, so let's look at the concept of a strong acid versus the concept of a weak acid. And we'll use two that are related, right? So we've got nitric acid. Stop it. Right? Nitric acid, when we put it in water, let's do it this way, right? When we put it in water, right, we'll immediately dissociate completely. This is a complete reaction to hydrogen ions. Clearly we're going Arrhenius here, and nitrate ions, right? And so, if we start off with an initial concentration of nitric acid of, say, 0.1 molar, it will all dissociate so that at the end we have 0 nitric acid left, right? And so if we start with 0 hydrogen ions in the water, then we're going to, right, it's 1 to 1. So our concentration, right, in the end, our concentration, right, if we look at the initial concentration of the acid, the concentration of the hydrogen ions is the same as the initial concentration of the acid because we've dissociated completely. This is a complete reaction or process. Okay? Let's contrast this with nitrous acid, right? HNO2, right? So when we put HNO2 in water, and I can truly put this as aqueous because HNO2 doesn't dissociate completely, and so it sets up an equilibrium between hydrogen ions and nitrite ions, right? And so if we do consider the same thing, if we look at our initial and our change, and in this case, we can truly make this E for equilibrium. Let's make it equilibrium, right? Because this is setting up an equilibrium. If we put in 0.1 molar of our acid, we end up at the end with about 6.3 times 10 to the minus 3 molar hydrogen ions. Which means we can fill in the rest of our table. Right? Let's see if I can get this right. So we end up with 0.0937, right? If I did my math right in my head, right? Don't leave nasty comments if I got it wrong. But most of our acid, right, if we look, most of our acid is still undissociated, right? Most of our acid is still undissociated. Only a very small part dissociated. It ends up that if we do this, it's about 6.3%, right? 6.3% of our original acid dissociated. Okay? So, let me take that back. Yeah, that's about right. 6.3% of our original acid dissociated as an estimate, right? And so we can see the difference between a strong acid and a weak acid. In a strong acid, the acid dissociates completely, so the hydrogen ion concentration is going to be equal to the original concentration of the acid, right? Whereas with a weak acid, the hydrogen ion concentration is much less, only a very small percentage of the original concentration of the acid, okay? Now, right, if we have an acid, and we will tend to use HA as our generic acid. In this case, we're going to use HA as a generic weak acid. It will set up an equilibrium between hydrogen ions associated with water molecules and its anion associated with water molecules, right? That sets up an equilibrium. And we can write an expression for an equilibrium constant, right? The K for this is going to be equal to the concentration of hydrogen ions at equilibrium times the concentration of the anion at equilibrium divided by the concentration of undissociated acid at equilibrium. And since this is for an acid, we call this constant a Ka, right? So the Ka describes the equilibrium of a weak acid in water. And usually these are small numbers. So for example, right, if we look at this, let's look at a couple, right? We talked about acetic acid, right? The Ka for acetic acid is about 1.8 times 10 to the minus 5, right? Much smaller, right? Very small. The Ka for nitric acid, or nitrous acid, excuse me, the Ka is about 6.3 times 10 to the minus 3, right? So these are very small equilibrium constants. And so we're going to have to talk about how do we deal with calculations when we've got very small equilibrium constants. So this video introduces acids, strong acids, and weak acids. The next video is going to talk about bases, strong bases, and weak bases.